like a specific product or anything, or a demo.
You know, it's strange because actually, perhaps the funding environment is different in the UK, because the people I chat to who are attempting these things over here, they're saying that actually the underlying ideas are less important to the venture capital funds here than the application.
Mm-hmm.
Which is, you know, well, which is maybe why more of the, until recently, more of the funding has been in California than in the UK. It's been hard to get funds for these early stage ideas.
That makes a lot of sense.
Right. Anyway, so maybe we should have a look at the watch and actually get Miles started with this second talk. Pleasure to welcome him back. And just as a brief introduction for those of you who couldn't attend last week, Miles has taken his PhD at UCSB, followed by postdocs with Steve White at UC Irvine and then at the Parameter Institute, during which time he worked on tensor network methods and the applications to topologically ordered phases and machine learning. He's now a research scientist at the Flatiron Institute in New York, and he's also well known as the lead developer for the open source iTensor code. And having added to this impressive list of achievements a notable pedagogical lecture on machine learning techniques last week here in this conference, we're now looking forward to his next talk, which will focus in more detail on promising future directions for tensor networks and machine learning. So with that, over to you, Miles, and we're looking forward to a great talk.
Great. Well, thank you so much for that kind introduction, Gunnar. And it's a real pleasure to be back talking to this audience. It was really nice to meet many of you in person in the student-led session, for example, last week. And I could tell from a lot of your really great questions that you have a lot of the right insights, I think, to you know, to be, I think a lot of you are going to be very successful. So it's really nice, a pleasure to talk to you. So this talk is going to be, as Gunnar said, a follow-up on last week, where last week I gave kind of like a lightning overview of you know, the kind of broad topic of machine learning, broad tensor networks. I kind of just touched on, you know, how do you put these things together, and then I showed some applications. But here I'm going to try to get a little bit more into the nitty-gritty. And so let me just start though by doing a bit of a recap of some things that we talked about last week. So we talked about machine learning, and machine learning is a technique that is data-driven. So this is sort of at least how I see it, that it's like some kind of process or some kind of framework or some kind of, you know, computer program that you feed more and more data into it, and it just gets better and better at some task. So that task could be reconstructing a quantum wave function given samples from say an actual experiment, like a quantum experiment. That would be tomography. Or, you know, it could be you feed images into some kind of neural network system, and it gets better and better at distinguishing the different kinds of images that you're feeding in, or maybe even telling you what kinds you should be even thinking about. And I introduced tensor networks, and this is a mathematical technique that has its origins in, largely in physics. And it's just the idea of, it's sort of like taking the idea of a low rank factorization of a matrix and blowing this idea really way up into exponentially big spaces of tensors and expanding the idea greatly. And the idea is you factorize a tensor within indices, which is really not something you can store or really manipulate efficiently at all, into a contracted product of many smaller tensors that say have 3 or 4 or 5 indices each, which you can easily store these individually, and then you just put them together kind of on the fly to reconstruct components of this tensor one by one, or in smaller clusters or things. And the benefits of tensor networks are really many. And I think we will understand the benefits even better the more broadly we apply them to other fields, not just machine learning, but they're already being applied outside in applied mathematics quite a bit. And these benefits include one I already said about reducing costs, memory and computation, both are important. And really gaining theoretical insights. I'm sure a lot of you are aware of things like, you know, a classification of certain like bosonic wave functions in 1D that can be done entirely in the language of tensor networks, for example, or things like understanding and classifying scaling of entanglement, which wasn't exactly done with tensor networks, but was very heavily motivated by them in terms of like why this would be a worthwhile thing to do and what questions to ask and so on, and what kind of implications it would have for efficient simulations. And then things that are a little newer to physicists, like filling in missing entries, given only partial entries of the tensor using the tensor network. And then, as I'll show it toward the end of the talk, that these come with many interesting and kind of elegant and powerful strategies to optimize them, whether that's for physics applications or otherwise. And then I introduced this idea. There's more than one way to do it, but there's a particular idea that I am pushing on, this idea of how to put a tensor network into a machine learning model. And there's different ways to do it, but I'm fond of this way where the tensor network enters linearly into the model. So the idea is that basically the model is some kind of just giant product of a set of basis functions with a tensor network. And so the tensor network enters linearly, and this kind of lets you bring over more of the algorithms from physics and also do a little bit nicer theory, I think. You could also put a tensor network into a machine learning model in other ways. Like basically anywhere there's free parameters, you could replace them by a tensor network. But this is an idea that's inspired a bit more by this older idea of machine learning, of kernel learning, or sort of generalized linear models. And I'll expand on that in just a minute. And then we discussed applications to sort of what are some of the state-of-the-art applications. And two of the most recent ones that literally just came out weeks ago are applying kind of coincidentally the same platform, the thing called a locally purified state. Here it is in a horizontal orientation, and here it is in a vertical orientation, to either anomaly detection and tabular data, which are these kind of like irregular data sets that are used widely across machine learning and getting state-of-the-art results. This is the tensor network result, and the boldface means the leading result in that row, or applying these to physics directly to do quantum process tomography, which is a really interesting topic. It's like reconstructing the map that actually led to the samples that are observed. It's like reconstructing this completely positive trace preserving map that's like a sort of like a noisy quantum circuit, but backing that out just from samples. So now on to today's talk. What I'll do first is I'm going to give a more kind of compressed review of machine learning, but sort of driving towards the idea of putting a tensor network in. So just to kind of show a different motivation for this. Then I will briefly, just in kind of 4 slides or so, talk about architectures beyond using matrix product states. Because one thing some of you who are interested in this topic might wonder about is, how can you use other things besides matrix product states? What would be a reason to do that, and what might you gain? Then I'll spend most of the talk talking about a specific direct learning algorithm for training MPS for a specific generative modeling task of synthetic data. So this is to kind of drive the idea that tensor networks let us slow down and kind of really do some actual like theory. And that theory here, I mean broadly in the sense of like coming up with alternative training algorithms that are rather different from ones in the past. And rather different from just stochastic gradient descent, which is the kind of go-to algorithm if you don't have another one to use. And then we'll see how also the setting of this algorithm allows us to begin to do some nice theory about predicting the generalization performance of this algorithm for that data set. And it's almost more like a sort of the beginning of a theory that I hope some of you might want to pick up and continue with and try to complete and make it better. And I'll tell you how I think that theory could be improved and made better, but already I think it's a promising start. Okay, so now, and now this is a good part, to stop me with questions if you have them, or if you see something that's a little confusing. But I thought I would just do another kind of lightning introduction to machine learning, but a bit more technical and like a bit more nuts and bolts, just to get us into the right frame of mind to discuss what's coming later. And so the setting here is to say, what are the kind of ingredients you need to gather together when you're doing a kind of typical machine learning setup? And so you need data. And usually the data is represented as some kind of vectors that are traditionally called X. So these are like the things you're going to input into the model. And this data could be training data, but then later you also will have test data that you'll use later on, way later on. So after you're completely done with training, now you finally look at the test data. But think of the XJs as your training data, which you can use any way you like to try to tune up the model. And then very often you have some kind of labels. You don't have to. So you might not have labels, and then you'll be doing unsupervised learning. But if you have labels, then that's the setting of supervised learning. So here it's convenient to talk about those. And the idea of the model will be to assign the correct label or output Y given an input an input X. So we want to map X to Y in the correct way, or get close to the correct Y. And then the main kind of centerpiece is the model function. So this is some function that we get to choose. For various reasons, we'll choose different ones, and later we'll have one with a tensor network in it. And the model function has adjustable parameters, and these are often called weights. And then the idea is that the other important ingredient is you have a cost function, and this can again be chosen in very different ways. Here's where a lot of theory happens about, you know, how to choose the right cost function, what the choice of cost function really says about why machine learning succeeds or fails, ideas about regularization and priors and all these sort of things. That's also contained in the model function, but there's some interplay between these two that's very interesting, and it's kind of a really where machine learning becomes like a science, I would say. But you know, you choose some kind of sensible cost function that is designed so that if you could minimize it, then it would map correctly the inputs to the correct outputs, and then you try your best to minimize it. So let's kind of go through those ingredients now one at a time. So the data set might be, say, images, and these images are made of pixels, and then you just rasterize it, so you just unroll it into some kind of one-dimensional format usually, and then you have these pixel values, and then you just get a list of numbers. And here I'm just showing grayscale, so the numbers, say, could be normalized to would be between 0 and 1, going from, you know, white to black or black to white. So that's your inputs, but the inputs could be other things too. It could be text, it could be audio, it could be irregular kind of data from a table or something. And then if you're in the setting of supervised learning, you have outputs. So let's be a little bit concrete here, and let's just say the outputs are just numbers. They're just real numbers. And so the outputs in this task I'm showing would be given images of 7s and 8s, handwriting of 7s and 8s. Let's distinguish a 7 from an 8. And then the outputs here are, say, the ideal output here is +1 if it's a 7 or -1 if it's an 8. That could be just an example setting. But the actual model, when you train it, could give output anywhere between, you know, any real number, and you just sort of say if it's greater than 0, it's a 7, if it's less than 0, it's an 8, that kind of thing. Now, the simplest model that really you should always start with, especially if you're learning this topic for the first time, is called the linear classifier. So this is one example of the sort of infinite zoo of models you could pick, but this is an important one to understand. And the linear classifier just says, why don't we just take the input vector and dot it with the weights? So make the weights to be a vector of the same size as the input. And then it's just a bunch of real numbers that we can choose any way we like. You dot it with the input and add a constant shift, which is one other trainable parameter that you have. And it works surprisingly well. So if you apply it at this task, say, of distinguishing handwriting of 2 digits, you'll be surprised how well it can work. Like often you can get things up into, you know, say like low 90% accuracy or something like that, which is kind of shocking for how simple this model is. But maybe you can understand why. I mean, you might see that all the linear classifier has to do is put some weights on these pixels, and then it'll say that if those weights contribute, I mean, maybe they have like large negative values, then you'll get the output to be negative for the 8s, but not so negative for the 7s, something like that. So the linear classifier can work for these simple tasks quite well. And then just to show you how this all kind of really comes together, a very sensible cost function to choose for this task is the squared error cost function. There's other ones too. But what this one is saying is that we can think of the y as some kind of idealized output function that given an input number j, and this is just enumerating the input. So this j runs over the whole training set over both 7s and 8s examples. It's some kind of perfect indicator function that it takes exactly the value +1 on a 7 and exactly the value -1 on an 8. So what the cost function is measuring is how far is our current optimized function from this perfect function. And it's penalizing us for not being right on top of this perfect function. But now, of course, we'll never be able to be perfect on top, but we try to get as close as we can. And so then here's just putting in the linear classifier and you know, putting it into this cost function. And you may have already noticed I made a slight mistake, which is that I left out the constant shift. So here I'm going to cheat and say that what I really did is I augmented the input vectors x to include an extra component that's always set to 1. And this is in fact often how it's done. And then that component of w will be the constant shift. You can do tricks like that pretty easily. Okay, so then how do you actually optimize these things? There's different ways. In fact, in this case, with this cost function in this model, you can actually write this whole thing down as a big linear algebra problem and just do linear algebra and solve for the w's in a sort of a single shot. So already in machine learning for a long time, it's been known that there are sensible like direct learning algorithms where you can just find the optimal weights sort of directly just through a deterministic algorithm. And this is one of those cases. But more often than not, you can't, either for reasons of efficiency or the problem just isn't sort of set up that way, where it's not obvious how to do it. So much more often you use the strategy of gradient descent. And many of you may know this very, very well, but others of you may not be so familiar with gradient descent or how it really looks when you do it. And it's a rather simple idea. You just say that, okay, we want to minimize this function. So we initialize the weight somehow, maybe just random numbers or something. And then we take the gradient of the cost function with respect to each of the weight parameters, just analytically. Or nowadays it's very popular to do this using automatic differentiation tools and software, because it can be very, very tedious, for example, to do this with very complicated neural nets, and it can slow down experimentation. But here it's very simple. So we take this derivative, the 2 comes in front, the minus sign flips the order of this term, and then the derivative in here just picks off the nth component of the x vector. So in the end, this is some sum that you can code, say in Julia or Python very easily. This is something you could just do this afternoon, where you just have your data and you sum over it with these. This is just a number times another number. You add these all up and you get some correction delta n, which is the correction to the nth component of w. And then the way you update w is you put some kind of empirical step size parameter here, alpha, which in machine learning is often called the learning rate, but in gradient descent, you would just call it like the step size. And you choose it to be something like 0.01, and then you just run this update. And you just run it over and over and over again, and you'll see the cost function coming down and down and down. And you'll be surprised how well this works to actually do things like handwriting classification. So that's just the idea of gradient descent. Now, how do you go beyond this? And this is where we'll kind of quickly get into tensor networks. What if that linear classifier is not enough, as it's often not? So, what if this kind of model where you have a constant plus just these parameters times each of your features, each of these x components one by one, just doesn't do the job? Well, then one trick you can do before investing in much more complicated tools like neural networks or something like that is you can do a simple trick where you can make an extended linear classifier. So what you can do is you can make additional features, because remember these x's are constants. These are just things that are in your training data that are given to you already, and they're frozen. They're not changing when you're optimizing. So you can make like an extended x that's like 1, x1, x2, x3, and so on all the way to xn. Then the next component of that vector after xn is the number x1, x2, and then the number x1, x3, x2, x3. So you can think of this as like some larger x input vector. Then you can think of w and v together as some extended parameter vector. But really, v is like an extra set of parameters now that are going beyond the linear model that weight these extra terms, which and sometimes are called interaction terms, if you like. But they're just additional parameters that are weighting additional polynomial terms. And you can keep playing this trick. You can keep putting more such terms. You could also wrap the x's up in nonlinear functions and things. But the weights still interlinearly, so you can still write down these kind of simple cost functions, even use linear algebra to solve for the w's and v's, if you like. But I want to point out that here the parameters still interlinearly, and yet this is manifestly a nonlinear function now of the inputs x. But remember, those are frozen, they're just inputs. So you could keep going, as I said. You could add third order terms, fourth order terms, other nonlinear terms. If you keep doing this and you write down the most general model of this type where you have different products of these x's, you arrive at this form. And then this is where this is one way you can motivate putting in a tensor network. There's other ways too. And so again, you see this is now a highly nonlinear function of x. We have products of all the different components of x in principle to different powers. But the weights still interlinearly, which gives us some nice abilities to do interesting training algorithms and interesting theoretical studies. Sorry, that's my buzzer at my door. Just getting a package. So the weights interlinearly, which can become important. Now, the weights have the form of a really large tensor, and that's intractable. We can't work with that. But if we can factorize this tensor, either because we know it's going to have this property for some reason, or we just do this as some kind of ansatz just hopefully, if we factorize this into a tensor network, the model will become efficiently trainable, and we'll see later what some other advantages are, like getting some insights into the model. And you can really use any basis of functions. So I showed the example of polynomials, where we could say take each x to the 0th power or the 1st power, or we could put the 2nd, 3rd power. Or you could use other functions. So you could use functions that enforce some kind of symmetry, or just give the model additional fitting power. So here, those ends would label not powers of x, but they would just say pick this function or pick that function to put into this sum. Okay, so that was just kind of a lightning overview again of how you can put tensor networks into machine learning. One way to do it, sort of in the framework of what's called kernel learning. If you want to get into that older literature, this part would be what's called a feature map, where you map your sort of raw features into some kind of extended features labeled by these integers n1, n2 through nn. And then this is the weight vector or weight tensor, if you like. So in a way, kernel learning is sort of just the idea of, probably if someone's a kernel learning aficionado, they might not like this description, but it's sort of the idea of just some kind of supercharged linear classifier. And it's rather different from neural networks, but it's known to work extremely well. It's just sort of run into some efficiency issues in the past, which is a big reason why neural networks overcame them in popularity in recent years. Okay, so now let's discuss a little bit. We talked last time about these models, but I showed you a lot of examples of people optimizing them using the case of weights, which are encoded as a matrix product state. But have people been looking at other kinds of models? And if they have, what are some of the advantages you can get when doing this, right? So of course, one advantage might just be you do this and you just find it works better because it's a more powerful ansatz. But I think there's some other interesting things to think about as well. So I'll show you some examples, right? So matrix product states are already a very good choice. They're extremely expressive. I think they're more expressive than people realize, in fact. Sometimes I'll hear statements like people will say, well, they just don't work for 2D. But in fact, techniques based on matrix product states are some of the best methods we have right now for 2D systems still, even as of today. Also, I'll hear people say they don't work, at critical points. Actually, they work extremely well at critical points. You can reproduce power law scaling behavior out to thousands of sites with very modest bond dimensions of matrix product states. So they aren't technically in the right class, but that's only detectable at sort of very, very long distance properties and sort of very fine details. So they're very, very powerful things. And they come with very beautiful methods to optimize them. We know the DMRG technique, but there's other ones too that you can do. And it's still kind of an active area of research. And they're well understood theoretically. Okay, but let's also talk about what are some other things you could put in instead of a matrix product state. So one thing you could put in is a mirror. Now this is something that it's not always such an obvious thing to do because Mira, I won't have a lot of time to introduce them, but they have some drawbacks over MPS that actually makes them sometimes less desirable. But if you are careful to work around those drawbacks, then they can offer some interesting opportunities for machine learning research, I think. So I'll show you one of those things that we tried recently. And so Amira, very, very briefly, a lot of you may already know it, I hope. But what it is it's a kind of quantum circuit where you have these two different elements. One is called a disentangler. And this is something that just maps two vector spaces into, again, two vector spaces, two indices into two indices, say in this binary mirror setup. Then you have these other elements called isometries, which map two into one. So they're more like a renormalization group step, where they actually reduce the number of degrees of freedom as you go upward in this process. Then you have another layer of these disentanglers, which just kind of mix these two spaces or these two, followed by another layer of isometries, which again reduce or compress the space, and then over and over again. So it's kind of like a real space renormalization group, but it also has these mixing steps that mix across different branches of this tree. The isometries by themselves would just make a tree, but the disentanglers connect different branches of the tree, and that fixes a lot of technical problems with real space renormalization. So that's sort of a just a lightning description of Amira. So the idea that we had, this is me and Justin Race in a paper we published in January, was to use Amira, but where we just fixed the Mira, because we didn't want to get into the whole business of optimizing Mira right away. This was sort of our first attempt at using it in some productive way in a machine learning setup. But we wanted to say, let's just fix a Mira to actually encode a discrete wavelet transform. And I won't have time to introduce wavelets, but basically what they are is there's some kind of like localized Fourier transform. They're things which are local both in real space and in like Fourier space, or like momentum space if you want to use physics terms. So they're kind of a natural fit for what mirrors can describe. And there's actually been a lot of nice papers by people like Glenn Evenly, Steve White, and others exploring this idea in physics applications. And so we borrowed that technology from them and said, we know from them how to encode a family of wavelets into a Mira, and let's just do that and fix the parameters of these Mira layers. So think of all these as just having fixed parameters. And then we have on top a matrix product state. And that's where we put our adjustable trainable parameters on the top. So, and this is an idea called a curtain Mira. I couldn't find the paper, but I remember there's a paper from a while back that proposed this ansatz, where you put an MPS on top. And then here, this is the input data at the bottom. So these little blue circles, what these are, is these are these maps phi. So the n index is the adjustable index here that is connecting to the Mira. And so this line taking over different values, say 1 or 2, is selecting this feature to use this feature or not, or use that feature or not, or so on, and making linear combinations and products of these to define the model. Now the idea we had was, let's use this on some kind of smooth data. So what we did is we used it on audio data. So here we actually had a very large number of inputs in the thousands, which were actually samples of audio clips. So you can think of some kind of waveform here underneath that's like the audio, and then it's being processed and smoothed by the wavelet layers, and then finally processed by this MPS to be classified. And we just did some kind of binary classification saying, here's 2 kinds of audio clips and distinguish this kind from that kind. And these are audio clips of actually environmental audio, where it's just people out at a beach or cars going on a street or something like that. And we just want to distinguish these 2 families. So what's the advantage of doing this? The key advantage of this setup, because of course you could just do wavelet transformations on your data without a Mira and then feed the results into an MPS. So why bother doing this in the setting of a tensor network? Well, the advantage is this, is that you can adapt the model even during training. So the key capability that we took advantage of, this was proposed in a paper quite a while ago by Michaela Dolphy and Matthias Treuer. They pointed out that if you make an architecture like this, you can do a controlled fine graining of a matrix product state backwards through layers. So we could start with a model that's sort of over coarsened, where we take too many of these fixed layers. So it's actually going to over blur our data and then feed that into this model. But the thing is, that model is very easy to train. It trains very quickly and already gets you into a very good range of performance. Then you can say, okay, well, we didn't quite reach the performance we wanted, but it was very, very fast and cheap to do this. So now we can take the weights we have, and without losing any of the progress we've made so far, we can controllably apply this circuit like in reverse onto this MPS. This part is trivial, applying this isometry. You just contract over this index. The next part resembles like a time evolution algorithm in physics. You apply these gates, and then you do SVDs, and you break the result back into a matrix product state. And when you do, up to basically machine precision, this MPS equals this tensor here, which is this MPS attached to this layer. And so you don't lose any of your progress at all. Then you can continue training with this more fine-grained look at the data and see if the performance keeps improving. And if it improves a lot, you say, okay, that was a worthwhile thing to do. And if not, it actually tells you that you're done. And so you're learning how coarsely or finely you actually need to look at the data to achieve your task without having to pay a big penalty up front. So that was basically one of the payoffs. The other thing we could see that was kind of nice, this is data that Justin collected. We could see that this blue curve, for example, down here, this green curve, these were models where we started off with more layers initially. The red one had relatively fewer layers, and we could see that the generalization was a lot tighter in the models that had more layers. So we could see that, for example, here, the solid curve is the results on the training data, and the dashed one is on the test data, and you can see it doesn't fall by very much. And just to show you a bit more of what's going on here, this is the initial percentage correct that you would get when you start the course model. Then you drop down one layer and continue training, and the percentage jumps up because you've let the model see the data in more detail. And so we're showing that you can already get good performance, then you drop down a layer, and then you get a boost of performance, which isn't surprising. But what's nice to see is how close you already were before, and then it just continues improving. That's basically just this paper in a nutshell. Okay, so this is now switching to a different work that's not mine. Sure, yeah.
Yeah, is one of the key ideas here that every single one of these red squares and the triangles is the same tensor?
That's correct. That's correct. So, well, actually, we did really 2 kinds of layers. So we actually had first layers where we had the disentanglers were trivial, and that was very simple. Then we had a set of layers where they were this more complicated wavelet family called the Dabashis 4 wavelet. But then you're right, Sam, that these were all the same at that point. So we had something like 10 layers where the parameters are precisely the same in these red and blue tensors.
Okay, thank you.
There's a question from Jan, actually.
Yes.
Maybe my question was just answered. I wanted to know what you choose for the mirror in the first place, but I think you just answered that.
That's right. I should have said it on the slide, but we chose it to be either Haar wavelet layers, which is this very simple, just averaging wavelet, or this Dabashis 4 wavelet.
Yeah, thanks.
That's right. And so a natural extension of this project would be to sort of gently introduce trainable parameters. I'm sure many of you might have thought of that already, to say that, okay, we don't want to maybe go right away into this business of optimizing a mirror fully, which can be like cumbersome and expensive. But although it can be done, of course. But what we might want to do is say, well, really across this whole layer, there's 1 or 2 angles that parameterize these isometries. And here there might be 1 or 2 angles that parameterize these disentanglers. And in fact, these angles might even be the same across these different layers. And we could certainly do some kind of gradient descent on those. So we could sort of gradually reintroduce more trainable parameters. That's right. One other quick comment is that technically, you can't efficiently contract this network in a technical sense, because as you apply these disentanglers and isometries downward, then if you think of this as an MPS at the bottom, the bond dimension will grow and grow and grow. So we do introduce a truncation there, but the thing is you can control that truncation as much as you would like and check that that's very much not affecting the results. Okay, that's just a technical comment for those of you who know about that. Now, another reason to explore models beyond matrix product states is expressive power. But here, the idea I want to underscore is that it's not just that you're blindly casting out to other models and guessing other models and saying, I hope it has more expressive power. But as Tensor Networks assist you with theoretical understanding as you do this. So this is just highlighting a recent paper from last year by the group of Ignacio Serac and with Jen Eisert and with Yvonne Glosser and others doing this work. And they were just doing a theoretical study, basically saying, we observe that there's multiple interesting ways, different proposals for how to express a large joint probability distribution of discrete variables as a tensor network. And one of them is the way you might think this is the way in physics, but that's actually not right. This is the way we do it in physics, which Lei Wang and others coined as the Bourne Machine, which I think is a great name. It's the idea that you have a tensor network that encodes amplitudes. And then the way you get the probability is by actually, here's the tensor network. You get the probability by squaring those amplitudes, right? So we all are familiar with that. There's a way, though, that's more familiar to mathematicians and more natural in that setting, which is you just say the tensor network just is the probabilities directly. So rather than encoding amplitudes, which you square, the tensor network is just outputs positive numbers that you interpret as probabilities. This one is a bit more tricky in the sense that what if the tensor network doesn't output a positive number? So what if you allow negative parameters or even complex parameters, and then you compress these bond dimensions a lot and you find that sometimes you get negative answers, then you might have to threshold those away. So often what's done is it's just enforced that you can only put positive numbers into these tensors, but then that restricts the ansatz quite a bit. And then this group also considered this interesting ansatz called locally purified states. And roughly speaking, this looks like 2 matrix product operator tensor networks back to back, but you can have other pictures of it too. Or maybe you can think of some kind of like ancilla qubits and some, you can have these kind of more quantum information inspired motivations as to what this is. But basically the important point here is you have the same tensors here and just their conjugates. So it's A1 dagger, A2 dagger, and then they're put back to back. And this form ensures things like positivity of the spectrum, if you think of this thing as a giant matrix and diagonalize it, for example, and other properties too. You can see in physics terminology, this has a lot of power because you could encode, say, a thermal state, like an infinite temperature state, where this is just an identity map between these two very easily. You could also encode something like a ground state density matrix, which would be an outer product of 2 MPS, also very easily. So this has a huge amount of power and flexibility. Now that's what this paper was mainly showing. They were saying, let's use the fact that this is all some kind of generalized linear algebra to get a theoretical understanding or a classification of which format has the same expressive power in principle or more. And so they found a way to kind of correctly choose the bond dimensions of each of these cases to be like a fair comparison between them. And they also considered all kinds of interesting cases. For example, putting positive numbers only into this unsquared matrix product state, or tensor train as it's called. Or you could consider the case of a Bourne machine with only real parameters, or with complex parameters as well, and the locally purified state, and so on. And I'm not going to go into the details, they're rather complicated, but they were able to show things like, for example, that the set of functions you could reach with just the non-negative MPS was fully enclosed inside what you could reach with the kind of real or complex MPS. And then also that the locally purified state is an extreme, basically that was my takeaway of a lot of it, was the locally purified state is an extremely expressive ansatz. So that's kind of like the poor man's takeaway, is just that this locally purified state is very, very powerful. And sure enough, the locally purified state was used coincidentally in these two recent studies I highlighted earlier. So there it is, or some kind of modification of it. And here it is again as this thing called a Choi matrix that's used in quantum process tomography. And so I don't think it's such a coincidence that these are getting state-of-the-art results, and they use the most powerful ansatz that was identified by these groups. Or maybe it is, but it's a nice coincidence. I think it's just a neat connection to see between all three of these works.
Well,
so that was just, yeah.
The mad one. That was a very nice talk by Philippe Corbeau's last week, who showed that he basically used the locally purified state to look at 2D PEPs at finite temperature systems. So that also works very well.
That's a great comment. That's great to hear. Yeah, so Philippe's talk is on YouTube, I believe. So everybody should check that out if you're interested in. Is that the one you mean, right? The one he gave to the European Tensor Network?
Yeah, that's right.
Great. That's great. Okay, that's a good comment. Excellent. So yeah, these ideas, it's nice to see them all kind of moving around. I think that this locally purified state's a really elegant ansatz. So now with the remaining time, let me get into this kind of nuts and bolts part about optimizing tensor networks. So that was just a brief section to say, there's a lot of reasons to go beyond matrix product states. And I think, how that's done best for machine learning is still a bit of an open question, but there's some promising directions. Question?
Yeah, there was a question in the chat from Imam Maye, who's asking, studying the AKLT chain is quite useful in the MPS context, since one can write the matrices exactly. Is there such an example for such an ansatz here? With, I guess,
I like that question. Sorry, what's the last part?
I guess I'm just supposing that he's thinking of exactly known forms of tensor network.
Yes, well, it may not be the answer you're looking for to the person who asked the question, but actually one neat thing you can observe is that there is an exact construction of an MPS, which it has to be paired with the proper feature map. So with this feature map, so if you do this 1x feature map, there's an exact MPS construction of exactly bond dimension 2, so very small bond dimension that gives you the linear classifier. And I think that's a really nice thing. So if you're say optimizing an MPS, and actually not just an MPS, but even if you're optimizing like say a PEPS or something, and you want to give it a good initialization, you can actually first train a linear classifier and then perfectly load this into an MPS and then use that to initialize another tensor network without any loss of performance. And you can make extensions very easily too. So I think just with bond dimension 3, you can get these squared features as well. Not to arbitrary distances, but say if you're doing 1D, you could get like nearest neighbor squared features like x1, x2, and x2, x3, and x3, x4, just by increasing the bond dimension of the MPS by 1. So there are these exactly constructible cases. It's a nice question. We'll see one other kind of here in a minute, but it's really a physics example if you like. So let's talk about algorithms now. So algorithms, for me, you might think that things are all about performance, and that's the question people ask often. They go, just how well does this work? And of course, that's extremely important. But I think now we're starting to see enough promising results to say, okay, these can work, maybe not better than everything and not all the time, but they can work well enough that they could really be useful in key applications. And I think that will continue to improve. But to me, that's also just not what it's all about with machine learning. And I think others would agree that we also want to know, we also want to do some theory. We want to know first of all, we want to capitalize on theory to develop more powerful training algorithms, right? So if we have a better theoretical understanding of these models and of the things going into them, like the tensor network, that will inspire us to have more power and better performance. But also, it's very important in real settings to know things like, how well can I trust this model? Sure, it got a high score on some kind of, cooked up academic data set or some kind of overstudied, thing. But what if we go and apply it to real data that we just saw for the first time, and we don't have this kind of training wheels of comparing to other people's results? Can we have some kind of guidance from the model itself, or from how we trained it, or something like that, that can really tell us, here's how well it's going to perform as we go out to unseen data? Or could we study, is there some kind of adversarial input to this model that's going to completely break the model or give some kind of nonsense output? Can we get a deep understanding of that, or how probable is such a bad event like that? And we also want to know, did we choose the right tool, right? Are we kind of guessing, or did we really pick a model that was really best fit for the certain class of data that we're studying? And so these are all huge questions that lots of people are trying to answer in different ways. But I think from my point of view, if I can editorialize a little bit, I've noticed that I think people are being held back sometimes by their tools. So people are asking these questions sometimes, but they're asking them in a setting that is defeating reaching very solid answers, And I'm not going to go into too much into that, but I think that's what you see sometimes. And I think these goals are just as worthy as performance. So I think it's actually even fair to say we would be willing to trade away a little bit of performance, not too much, but it's okay to trade away some if you could gain, say, an understanding of how well the model would generalize, or if you could gain some kind of assurance that the model isn't going to give some kind of wild output for some kind of very tame perturbation to your input or something like that. So I think these are very worthy goals. So let's kind of see how we can make like baby steps towards some of these goals in this setting of tensor networks. And others are doing this too, of course. But I'll show you one path that I think is interesting. And we'll do that by studying some training algorithms a bit more systematically and seeing how some other people are studying these algorithms. And we'll see how one nice thing to do that should appeal a lot to physicists is to take toy data, toy models. It's like how we've studied the Ising model, for example, in physics and learned so much about, integrable systems and critical behavior and all kinds of things from that. I think similarly, we should be doing that in machine learning. And so we can use some synthetic data, the even-parity data set, to make it well posed about what do we mean when we say the model works or doesn't work. I mean, we have to have some understanding of the whole distribution to say that. We'll contrast these two training algorithms and then show a little bit of a sketch of a theory that predicts the generalization performance of the second of the two algorithms. So the synthetic data set that we'll look at in this part, the rest of the talk, is this data set called the even-parity data set. It's actually closely related to the GHZ wave function, just as a side comment. And what this is bit strings. So these are just, this data is just strings of bits, 0 or 1, of some fixed length, L. So here I'm showing L equals 10. And it's defined as all bit strings that have an even number of bits that are set to 1. So here we have all zeros, and here we have 4 ones. Again, we have 4 ones. Again, 4 ones. We could have 6 or 8 ones, or we could have all ones. So we just only admit bit strings with an even number, and if they have an odd number, that's not part of the data set. So this is actually a very challenging data set. It doesn't have local moments that are meaningful. So if you look at the average of any single bit, it could be 0 or 1 with equal probability. And if you look at correlations between neighboring bits, they could be all 4 different values with equal probability. So there's really nothing you can see locally about this data that tells you anything useful. So it's very challenging in the sense that you have to, the kind of proper way to learn it is you have to sort of start from the first bit, say, okay, it's even, let's say this one, it's odd. And then, you remember that you saw something odd and everything so far is still odd. And finally you get here, even, odd, even. So you have to really kind of scan through globally the whole thing. Okay, so let's keep that in mind. That's the data set we're going to use. The other ingredient is that we're going to choose a framework to represent our probability distribution. And people coming from quantum physics just think, well, obviously, this is a wave function and we square and get the probability, but that's not really such an obvious choice. We could study it by studying tensors whose output just is the probability directly. But actually here we will study this in this Bourne machine setup where whenever I show you an MPS, the setting here is that we will be interpreting the squares of its components as probability. So just to be clear, that's the setting that we're in. So what we're seeking is an MPS that if we sampled from it in the sense of drawing from this distribution where we square the MPS to get the probabilities, so just like a wave function in physics, we want an MPS that generates this set of bit strings with uniform probability. And kind of getting back to this question of, do we understand whether our model fits the data or whether we're using a model that's appropriate for this set of data? Here we do. So here we actually know that this data set can be fit perfectly by an MPS of bond dimension 2. So this is just the statement in physics that like the GHZ wave function in the X basis is a bond dimension 2 MPS, or in any basis really, of course. But that's just a statement for the physicists. But you could also just think of this as purely a statement about finite state automata, where this MPS, if you dig into this exact MPS form, basically what it does is it puts down a bit with 50-50 probability, then it remembers what it did. And it tells the next tensor, so far, things are say odd. Then the next tensor says, okay, great, things are odd. Now I put down a 1, now things are even. And it tells the next tensor, okay, now things are even. And then so basically they just have to communicate to the next tensor one of two things of whether it's odd or even. So that's why the bond dimension is 2. That's basically the reason. So we already know that if we're looking for an MPS, we are looking in the right class of things. And so this may make it seem a little too trivial, like that sounds too easy, like we're gonna find an MPS of bond dimension 2. But it's not so trivial because we're not gonna have all the data. And well, we could also not be sure what the bond dimension is a priori. So we wanna see that if we choose 2, we get good results, and maybe 3, the results start to degrade or overfit and things like that. So it's not such an obvious thing actually. And now there's lots of ways we could go after and try to find this best MPS from just samples of the data. And let's discuss 2 of these ways. So one of them is the idea of alternating optimization. So in math, this is called alternating least squares. In physics, this is what we would basically call DMRG. And then we'll also talk about this density matrix fitting algorithm. And I'll have to be a little bit brief for the sake of time about the first one, so we have time to get into the other one. So the alternating optimization is just the simple idea of saying freeze most of the tensors, and then update them one at a time. So just we're only going to update tensor number 2. So what we'll do is for each, if you write down pretty much any cost function, let's think of the squared error cost function, and you kind of write down the gradient, you do the chain rule through, and what you always end up with is your weights times your data. The data here is encoded as these, here I'm being a bit sketchy, but they're basically these vectors you attach to the MPS that can take one of these 2 values. So that it's either like the E1 vector or the E2 vector, 1, 0 or 0, 1. I'll be more clear about that in a minute. You attach that to your MPS, this is just a number. But then you take the gradient with respect to say the second MPS tensor. What that does is because of linearity, that just removes the tensor. So you just use standard rules of calculus, and you see that that is the same as removing that tensor and contracting everything else. And when you do, you get another tensor that has these 3 indices that are sticking out here, and that's proportional to the gradient. And you can figure out the proportionality constant, although it's not too important because you're going to use an empirical learning rate anyway if you do gradient descent. So then you just update that tensor by putting in some percentage of that update of this gradient tensor, and you just go tensor by tensor and do this. And you get a method that's linear scaling in the training set size because you just loop over all the data and do this, and it's linear in the length of the MPS because you just go up and down the chain back and forth. And that can work rather well. So this was used by James Stokes and John Tarula to study this data set that I'm talking about, this even-parity data set. They wanted to use it as a kind of a test of their ideas. And what they actually did is they actually found that for this setting of generating data, so not supervised learning, but it's unsupervised learning, that they could actually devise not just a gradient update, but in fact a locally optimal update, which is you basically sum over all the data, leaving a tensor out, and get this thing called phi, and then you just normalize phi. And they were able to show that that's actually the optimal thing to do, given the best possible other tensors that are frozen. Now this can still fail, but if you have good tensors that you're freezing, this is the optimal update for the one that's missing. So they were able to show that. Then they did a study showing how if they fix the bond dimension to different values, then here's the perfect result down here in green. Then they get sort of optimal generalization for a fixed training set size for smaller bond dimension, and then it gets worse and worse and worse for larger bond dimension. So the method was able to tell them basically, something about the bond dimension you need to choose to get the best results. So that's a nice paper from just last year. But alternating optimization is not totally the most ideal method you could want. The biggest problem with it is it can get stuck. So if you don't have a good guess for the tensors initially, you can kind of get into these infinite loops where the bad guess gives you bad updates, which gives you further bad parameters, and you just kind of go around and around and around. So it requires a good initial guess to work. Also, the results depend on how long you run the algorithm. You know, you run and run and run, the results are getting better. Should you stop? How do you know? So that's not such a big problem, but that's something that is not totally desirable. So are there other algorithms? Is this all we can do? Fortunately, there are. So here's one other one that I'll tell you about, which I would call the density matrix algorithm. It's basically the idea that an MPS is just a giant chained SVD, singular value decomposition. And so here we're just going to do a lot of SVDs, but in a certain way that's suitable for this setting. So this algorithm is a deterministic algorithm. The idea is that you write down some kind of perfect answer that you would already know would do a great job of classifying your training data. In fact, too good of a job, we'll see. But then you say, all we have to do now is just compress this thing into an MPS. So we just do a bunch of linear algebra steps, and then when we're done, we have an MPS. And we don't do gradient descent or anything like that. And because every step of this algorithm is just doing a sum, doing some linear algebra and repeating, we could, we meaning me and Ty Dene Bradley and John Torilla in this recent paper, could come up with a theoretical prediction of how well this algorithm would generalize. So we kind of picked this algorithm so that we could do theory on it. And it's just an interesting algorithm to try on this kind of data too. Okay, so let's review the algorithm and talk about this theory. So in a little bit more detail, when I say we're going to, map this bit string data to tensors that we can then apply an MPS to, or think about working with tensor networks. Again, what I mean is if we see a bit 0, we're going to map it to a vector 1, 0, or 1, we're going to map it to a vector 0, 1. So then when we map a bit string, it maps to something in physics we'd call a product state. In math, you might call a rank 1 tensor. Here, rank meaning that there's the bond dimension is 1 going through. So we can map all the data in this way to these kind of product state looking tensors, sort of like an MPS with bond dimension 1. And then from this kind of mapping, we can define what you might call a target tensor. If you want, you could think of it as a training set tensor. And it's defined to be like some kind of pure state wave function that perfectly overfits the training data. And we'll see in a second why that is. So let's say we have n elements of our training. Our training data has n samples in it. N could be 10, or it could be 100, or it could be 1,000. And what that is here is this is 1,000 different even parity bit strings. But that's a tiny fraction of all possible even parity bit strings, right? There's 2 to the L-1 possible even parity bit strings. So it's a huge number in principle. And we take this fraction, and then we produce these product states for each of the examples we have. And then we do a formal sum of them all. Formal, because you can't really afford to do this. You would get a tensor that would have L indices, and you wouldn't be able to store it for much bigger than L equals 10 or so. But we just think about doing this equal weight superposition, but don't really do the sum. You just think about it on paper. And then this tensor, this kind of funny wave function that we don't know much about, would overfit our data. Let's see why. So let's say if we ask, what's the probability of generating a particular bit string? Like say this one, 0, 1, 1, 0, 0, 0. What's the probability? So that's defined in our setting as this number, where we do the overlap of that with our model and square to get the probability. So then we just unwrap how we defined this tensor in red. And we defined it as being this equal weight sum over all the bit strings. And if our bit string is one of the ones in the training set, then it will appear here on the bottom. And when it does, we'll get 1. Otherwise, we'll get 0, because all the bit strings are different. And they only occur once in the training set. And then when we get that one element, the 1 over root n prefactor will square to 1 over n, and we'll get exactly the probability that we want. So we see we have 1 over n probability of generating one of these n elements of the training set. Otherwise, we don't generate anything else. So it sort of perfectly overfits. So that's interesting, but we don't actually want that. But the idea is if we can get close, yet kind of regularize the model by getting close through an MPS of some finite bond dimension, maybe this will generalize. Maybe we would generate a lot of the training set and the training set and a lot more. That's the hope. Okay. So how are we going to do this? How are we going to compress this really big sum, which could have some arbitrarily large entanglement if we think of it as an MPS or as a wave function, into an MPS? How are we going to do that in an efficient way? So we can do that in the following way, and I'll have to be brief, unfortunately, but maybe we can discuss it more later. What we can do is we can say, really, all we have to do is think of this big tensor as a matrix where we say that's the row, and these other indices are collectively a column. And then we do an SVD, and we cut there, meaning we just fold it into a matrix and then do an SVD. And then after that, we do an SVD here, 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 here. Then we remember that one way to do an SVD is to square a matrix. So you say if these are the row indices and these are the column indices, and then we just square the matrix, what we get is a much smaller thing. And if you diagonalize it, that gives you the U of the SVD. Remember, in SVD, you factorize a matrix into U times S times V dagger. This is sufficient to get the U. And the idea is we can get the U from a very small object, as long as we can just get our hands on that object. That's the philosophy. And we can, because the idea is this is a sum. So we can remember that the tensor is a sum. And here it's a double sum because the tensor appears twice. That's one drawback of this method, is you have to do a double sum over the data. So you do this double sum over the data where you trace over the indices that are not involved in the first step. And when you're done, you get a very small thing. It's just a 4x4 matrix. And if you diagonalize it, that gives you the U of the SVD you would take, and that's already the first tensor of the MPS. So here's a slide showing that idea. So we take the data, we do this double sum where we trace over all everything in the suffix, and we only hold this sort of 2 prefix bits open. And then we get this 4x4 matrix, we diagonalize it. It's by construction Hermitian and positive semi-definite. And so we can diagonalize it and it'll have positive eigenvalues. And we also truncate. We enforce that we only keep the top 2 eigenvalues. That's just a choice of how we do the algorithm. And then we take the diagonalizing unitary, or at least the first two columns of it, and that actually gives us the first MPS tensor that we seek. And how do you show this? We could discuss this more in the questions, but you'll have to just trust me that you can show that this is like an optimal way to get the first MPS tensor. Then you can take this unitary, or now it's an isometry because it's sort of been chopped off and you just keep the first 2 columns. And you can use it to, in physics terms, renormalize the data. I guess in math terms, you would just say change the basis from this original basis into this like compressed basis. And so what you do effectively is you reduce the number of indices you have to deal with, and you have this kind of summary index that summarizes what the first 2 bits are, or what's the relevant information about the first 2 bits into this new index. And then now you see that we really are back to the same position where we have a sum over these kind of product states with 1 fewer bit, 1 fewer site. So now we just open up the next 2 sites, including this kind of summary bit and the next bit, and just repeat the algorithm. So we do this double sum, trace over all these suffix bits, get another matrix, which now is actually still 4x4, but in general, it would be bond dimension times 2, size matrix. And then we diagonalize it, get another unitary or isometry, and then put that in as that gives us the next MPS tensor, and so on and so on. You just keep looping the algorithm and getting the next tensor. So you actually get the MPS tensors 1 by 1 by 1, and when you're done, and you just go across in one pass. And so you get a deterministic algorithm for generative modeling, which is nice. And what's also nice is that truncating each of these density matrices, these row matrices, is how you get the bond dimension of the MPS. So it's actually adaptive in the sense that you can expect these eigenvalues and see how many to keep dynamically, or you can just sort of try the algorithm with different truncation settings. And what you're doing, interestingly, is you're intentionally making an error here, in the sense that you're intentionally missing this target tensor. If you actually kept the whole target tensor, you would overfit by definition, and you would not generate anything outside the training set. So the fact that when you do this, you do generate things outside the training set means that generalization here is coming from the so-called error that you're making. So here, compression is learning. It's like the fact that you're compressing the model is how it learns, is why it learns. So we're often thinking of this compression of throwing out a density matrix eigenvalues as something regrettable in physics. It's like an error, but here it's actually the key to the whole thing. So I think that's very interesting and nice. And I think this is an example of what I mean by kind of doing theory with tensor networks, where there's a huge conversation going on right now in machine learning in the setting of neural networks about why do they generalize? What is driving the generalization? And there's all these ideas about, well, maybe it's the landscape of the cost function and the dynamics of stochastic gradient descent optimization and these things, but they're a little hard to get your hands on. Here, I think there's an opportunity to get our hands more directly on what is actually making the generalization happening. And there's some nice work by people like Surya Ganguly, not in the setting of tensor networks, but who is kind of hitting on some similar ideas about maybe it's truncation of SVDs, this kind of thing, low rank factorization that's driving generalization. How well does this algorithm actually work in this setting? So what's shown here is the fraction of the data set of the bit string, this even parity data set that we use as the training set. Of course, we run over and over and do different random fractions, different random samples for lengths of 16 bits. And this shows the distance to the true distribution using this kind of Bhattacharya distance, which is just related to the log fidelity that we know in physics. And it's just showing that first the distance is terrible, but then as you get to this fraction of 0.025, it becomes very, very good. And you get into, down here, you get into the regime where you have something like a less than 1% probability of generating an odd parity bit string. And then it comes down even further to sort of a 0.01% probability of generating the wrong parity. I kind of ran out of time, but let me just kind of flash through just to give you a quick idea about, now we did this partly because it was just interesting to do to get these results, but we also did it because we could study this algorithm and really dig into the algorithm. So this was credit mostly to Ty and to John for really coming up with all this part, with just me giving some comments. And the thing they did is they said, okay, let's sort of step through each step of the algorithm, but try to understand theoretically what's going on, in the sense of we understand this data in detail and we understand the algorithm in detail. So what can we say? So we could make observations like that all these reduced density matrices, which are summed over these, trace over these suffixes, have a block diagonal structure. And that has to do with the fact that there's sort of even and odd parity sectors. It just means that the suffixes, if the prefix has even parity, the suffix also has to have even parity. And it has to match the other string below, otherwise you get 0. So then the prefix here also has to have even parity. So that naturally groups the non-zero elements into these kind of even parity block and odd parity block. That was one observation. Now we made an assumption that the two dominant eigenvectors we're going to keep always come one from one block and one from the other. It's not always true in practice, but this is where you can see we could improve our theory in the future. But in the limit of using more and more and more and more training data, this becomes asymptotically true. And then we parameterize these two dominant eigenvectors in some arbitrary way, just in terms of two angles, theta and phi. It's just a parameterization. It's just the way to parameterize two component normalized vectors. Now, the key thing John and Ty did is they said, given a particular reduced density matrix with these elements, which are the only possible non-zero elements, how do you find these angles? And you just do some algebra and you find these are the angles. And what that reveals is that the key thing driving, I'll say it on the next slide, the key thing driving whether these angles come out well or not are these quantities they call gaps. Not gaps from physics, but what they mean by gap is basically the difference in frequencies of prefixes. So basically D1, D2, D3, D4, all that's saying is as you loop over the data, how often do you see the prefix 0, 0 versus 1, 1 versus 0, 1 versus 1, 0? And the difference in this, the mismatch in those frequencies, it drives these gaps. And what they found is that as long as these off-diagonal elements are non-zero, which almost always happens, then all the error in these angles comes from the fact that these gaps are not zero. So basically, it's the fact that you have slightly different populations of these 0, 0 prefixes from 1, 1 that drive essentially all the errors in the learning. So they could see what's really driving the errors. What about the deficiencies of the data is making errors happen and how much? And then kind of skipping ahead, they could come up with expressions for sort of the typical value of these gaps. And then they could sort of propagate the error through and say, just using statistics of these data sets, what is the typical value of this mismatch? What's the effect on the angle of these eigenvectors? And how much error does that lead to? And then we could come up with a theory that says, and the theory doesn't work so well here, but actually that's not even where you want it to work well. You really want it to work well once the model starts to work well enough and kind of in this limit of more and more data. And it really comes together very nicely. And you see that the theory predicts, just as the experiments show, that the training starts to get good around this particular fraction. As you zoom in more and more on this tail, they really match quite well because this is on a very, very demanding scale. It's like this kind of fidelity, measure. And the theory and our experiments match very well about how close we get to the ideal result. And in fact, we even know a couple of reasons why they don't match perfectly. It's something about the way we did the theory in particular. Basically, the averages we did are slightly inequivalent. So we even know why they don't match perfectly. So even that we understand. And if you want to see an expanded and much more detailed discussion, I'd encourage you to look at Ty's PhD thesis, which is on the archive. And she's a very gifted communicator with a very, she likes to draw these really great figures and illustrations. So I encourage you to check that out. And then I'll conclude the last two slides here to say that I hope that kind of whetted your appetite for seeing what you can do with tensor networks in the setting of machine learning. And I think there's a lot of ways we could develop this theory I just showed and make it a lot better. And one of them would be, I think we could, instead of just getting close to the experiments, I think we could actually derive rigorous probabilistic bounds, lower and upper bounds, or maybe at least one of those two bounds on these experiments. We could also, of course, apply this same setup to many other classes of synthetic data. So you could imagine other bit string data that's made up, but which has really different properties from the even parity data. And we could see start to see, how well does these techniques generalize, and what settings of what kind of data do they generalize well for and not generalize well for. And then it would be really neat in general going forward, and this is kind of even going beyond MPS, to be able to take some data out in the wild, like real world data or data from physics experiments. And then just by studying some kind of summary statistics of the data, just get some local moments and maybe do some kind of, Monte Carlo to sort of estimate the entanglement entropy, if you will, which would just be like the rank of it thought of as a matrix, to say how likely is it that we will be able to learn this data, and for what complexity of model, for what size of MPS, and so on. That would be a really nice, like, sort of, ultimate goal, I think, to go toward. So then, in summary, really, of the whole talk, I hope I convinced you again that tensor networks are interesting things to use to do machine learning, whether for physics or real world data. They have a variety of training algorithms, and they really do offer theoretical insights. And sometimes we can even get state-of-the-art results on a variety of tasks, like I showed you these recent papers. And I think most importantly, even if the performance isn't always state-of-the-art, as long as it's close, the most enticing thing to me is that we can really ask deep questions about things like generalization and algorithms. All right, well, thank you for your time.
Well, thank you very much, Miles, for a great talk. So let's put our hands together for you. Excellent. So yeah, I already have one question in the chat here. Anybody else has any questions? Just make them known to me, or just post them in the chat, or raise your hand. So the first question goes to Sam Carr.
Okay, yeah, just thanks for another great talk. But actually, this last example I gave you, I was wondering about what might be quite a deep question about what is meant by the simplest thing that brings all these things together. Because particularly for this example, you said there's no local correlations, there's no nothing. As humans, we can easily say, well, it's the overall number of ones is what we're looking for. But with any finite data set, there's presumably other complex correlations that the computer may or may not find. And one may then further think that perhaps choosing an individual tensor network or something will put a bias onto something rather than something else. But some of these results you were showing seems to show that's not so much the case. So can you just learn something from this by what we mean by simplest?
Yes, I think that what you said really already is the right answer for my limited understanding of all this, is that I think it's like you said, about that there are extra spurious patterns in the data that have to do with what particular samples were included or not. And that's an idea that comes up in this idea of recommender systems and low rank techniques to do learning, like when you kind of do movie ratings, this sort of classic example. And there, the idea is that these extra patterns that are spurious, that are just to do with the randomness of your sampling, they make the matrix to have full rank or high rank, meaning the number of singular values that are non-zero is huge, but there's a long tail of very, very small singular values. So it's like these things happen and they're there, but they also have very low probability of kind of, or they sort of have a low like explaining power of sort of explaining all the other correlations that are there. And so they come with very small singular values. And so throwing them away, that's kind of what the learning is, from my point of view in this case, is that by throwing them away, you are throwing away information that's in the training set, but it's training set specific information. It's only to do with that one training set and not any other typical training set you would get the next time or something.
Yeah, sure.
But I don't know if that was toward your question all the way.
No, it is. But I think somehow that also is, I'm just interested in what that teaches us about being humans in pattern recognition, because I mean, I certainly don't feel consciously I'm doing an SVD and throwing away low weight eigenvalues when I look at something and say what's common between these two things. But apparently that is sort of what I'm doing, which is just curious.
I mean, that's right. I mean, so I think that just as a broader comment, I hope that we've seen this in physics, of course, too, right? And in fact, tensor networks are an example of this in physics, where having a new set of tools facilitates new questions, right? And I do want to emphasize that some of these questions have been posed and answered already quite well in machine learning about low rank methods. But, here with tensor networks, we sort of get a chance to do that on steroids with, these kind of multilinear low rank, high dimensional low rank ideas. But you're right. I mean, the fact that it inspired you to ask these questions about learning and the brain, I mean, that's what I think we can get when we do this theory.
Cool, thank you.
Great. We have a next question here from Jan van Delft, who is asking how to optimize the ansatz using locally purified states, as that seems to be a highly nonlinear optimization problem. How does one approach that?
Good question. I may not have a very deep answer to it. I think the good news is that all these different tensor networks, you can always do gradient descent, and I'm sure Jan knows that's always possible to do. So one can always just hold out one of the tensors and feed in the data and kind of compute the gradient efficiently. So I guess I should go back to that one and we can just look at it, and then. And I can recommend, if you want to see a paper where they do this kind of thing, the paper by the Google group, the Google X group, they discuss, I think they could put a little more details in their paper, but they have some details about the steps. And so basically one just can hold out this tensor, contract everything else efficiently, saving all these partial contractions here down to this whole, compute this gradient and update. Now, then one would also have to carefully enforce that these two tensors remain the same afterward, which one could do just by once you update this tensor, now just force these to be a copy of each other, or just a dagger of each other, which is a bit of an uncontrolled step. But all this can be done with kind of a damping and like a learning rate, like a small step size. But that to me, I was actually thinking about it this morning, like, could we do a better algorithm than that for these LPS? They're so close to being MPS. So maybe by some kind of local deformations, we could merge part of it into an MPS temporarily and then break it back apart. But of course, one has the challenge of it has loops. So it might be like similar to working with the PEPs where there's sort of difficulties there.
Sounds good. So we have one more question here from Joseph Sykes, who says, who asks for a good review for both physics applications and general machine learning. Do you have a recommendation for that?
Specifically about tensor networks or otherwise, I guess. So let me see. So I would say a really good review in a general way. Let's see, I think I'm only sharing my, just my Keynote screen. Maybe I can switch to my browser as well. Let me just do my desktop.
You could put a slide in maybe at the end of your presentation when we upload it.
Okay, that's a good idea. Okay, that's a good idea. And so basically there's this article by Pankaj Mehta, David Schwab, Marin Bukov, and others, and I can put a slide in, that is a, I think they call it like a high bias, low variance introduction to machine learning for physicists. Really excellent article. It's basically like if you understand everything in that article and it's explained very clearly, then you're already like, it's like you get a master's degree in machine learning essentially or something. It's it brings you very up to date with sort of what are the key things in machine learning to know to sort of become like an expert on, at least to get started with that topic. Now, in terms of some of the specific things I'm talking about, I think no, there's not really such a review yet, but that might be coming. So thanks for the question.
Excellent. So the next question is from Andrew Green. Do you want to go ahead, Andrew?
Yes. So Miles, could you comment on the existence or otherwise of barren plateaus in your optimization scheme you talked about at the end?
So do you mean the second one? This density matrix one?
Yeah, the one that, yes, this density matrix one.
Okay. That's a good question. I don't know totally if the idea of plateaus is operative here in the sense that one's not making, the kind of small moves around on a cost function landscape in that sense. It's a great question though, I mean, to think about, like, because the learning can fail. I mean, even though I was saying, oh, it's deterministic and this kind of thing, that's true, but it's kind of true more in this like asymptotic limit of, it is true in the sense that you definitely get an answer and it's sort of just predetermined when you run over the data. It's just that it can be very poor, as you can see down here. but it will asymptotically get better as you put more and more data into it. And so at least in this setting, we were able to see when a complete failure could happen. And by the way, this is another bit of theory that I liked out of this that we didn't follow up on, but here we focused more on just what's the typical performance. But another thing that, of course, in industry, you would really want to know, like let's say you had a machine learning system that was controlling an airplane or something. You would want to know what's the probability of kind of catastrophic failure to happen. And that's driven by the absence of these off-diagonal terms. So if they're absent, then you get a completely catastrophic failure of the model. So in that sense, Andrew, that could kind of be like an analog of a barren plateau in the sense that you have some kind of setting where the training is just never going to succeed. Otherwise, I don't think there's anything in this setting quite like the analog of like an initial guess, where you really are starting somewhere in parameter space per se. It's more like you just have the data.
I see. So
that's your.
So if I could paraphrase to make sure I've understood, it's a deterministic scheme, and if you incorporate all the data, then you're going to get there. But if you're to the extent that there is any stochasticity, it's in your batching. And the question is whether if your batch is too small, that's the equivalent of the barren. So yes. In fact, would I interpret that point on your curve at, I forget what it was, 0.025, as the point where you get beyond the existence of barren plateaus?
Probably so.
Interpretation, or
probably so. We didn't quite dig into what makes this point what it is, in the sense, I mean, other than we had the theory, and the theory also, agrees, but we didn't quite see if there's really a sharp effect happening there per se from the theory. But that probably is right. I mean, we could even look a little bit. They had this expression for what's the expected value of these off-diagonal elements, and so maybe one could basically say, we could say the probability of this one actually being 0, from the statistics, what is it, and when does it sort of go below a certain threshold, and so on.
I see. Thank you very much.
Thanks, Andrew.
Okay, so we have another question here from Sung Sup Lee, who asks, the tensor networks shown so far would correspond to the states, pure or mixed. And then can we define a Hamiltonian in the context of machine learning?
So it's a good question. So I think it's like, I would give 2 levels of answer. And the first one, I would challenge you to say no. I'd say, try to not always, I don't think we have to think of Hamiltonian, because here we're using tensor networks as like, just sort of like how you would use a matrix, right? So imagine if physicists were the first people ever in history to use matrices, and then nobody in math or something had used them. Like here, that's not quite true, because people in math have used tensor networks too in the past. But let's say that was the case. And then one day someone was using a matrix to do like a least squares fitting, and someone said, what's the physics of this least squared fitting? Well, you'd say, it's just a matrix, So similarly here, that's one level of answer. But I think another level of answer is that we know one of the nice things about tensor networks, at least in matrix product states, is you can always deduce a parent Hamiltonian from a finite bond dimension MPS. So you can always produce some Hamiltonian that for which that MPS will be like a frustration-free ground state. And so I think that is a really interesting thing to think about doing. So, take data, find an MPS, then produce that parent Hamiltonian, whether or not this MPS is a ground state of anything in real life. And then, try to understand, maybe that Hamiltonian is like some kind of tool that one could study as some kind of process to generate other data, or maybe the gap of that Hamiltonian tells you something about the speed of training or something like this, so I think there might be interesting questions.
Excellent. So the next question is from Timotheus Tula, who might just want to go ahead and unmute himself.
Right. So I wanted to ask you about this even-parity set problem using density matrix algorithm. So could we apply some concepts from information theory to compare your results of minimum percentage of the total data set needed to get the probability distribution right? Like I was thinking about something like error correction codes where the problem seems to be very similar, and we can get a finite answer for that.
Yes, I think that's a great idea. And I'm not such an expert on codes. Like I'm aware of kind of some of the ideas, but I don't know if I can comment too well about that connection, other to say I encourage you to to pursue that connection. I think there probably is actually something quite nice to do there. Now, in terms of information, I'm quite certain, yes, that I talked about this exact result. I mean, the slide doesn't have a lot of information on it, but just something for us to look at. That we were talking about how one can definitely understand the reason why the bond dimension 2 is enough is that the only information that has to be passed left and right through the system to coordinate all these bits to have even parity is just what is the parity of the other half of the system. So this bond just has to tell, this half has to tell the other half what parity it has, so they can coordinate and make sure that the total parity becomes even. So we can definitely see that that's an information theory kind of thing going on there, where they're just communicating the minimum amount of information to coordinate on this task. So I do think that is something that could be fruitfully explored more, like to think about automata or some kind of rules that say, okay, this part of the MPS is going to do something over here, and this part's going to do something over here. And then they just have to kind of minimally coordinate to make sure that what they do is compatible and leads to a sensible answer. So I think that could probably be explored a lot more. And I think there's even some recent work kind of about this type of thing by, I think it's Jim Cuevas, who's doing this about spin models using automaton picture to classify classical spin models, and that could sort of connect a lot with classical data. So basically, yes, I would say I'd encourage you to pull on this thread some more.
All right, thank you.
Mm-hmm.
Brilliant. So with that, we should probably slowly draw things to a close. So I know Miles, as John, will also be back later in the discussion session, probably. So students can still ask some more questions then. And in the meantime, let's thank him again for a great talk and for making it very pedagogical.
Thanks for the great questions.
Right. So we will be back